Let's take a look at one of the applications of the determinant, and it's called Cramer's rule. Now, Cramer's rule is a method for solving a system of equations, like this one, for example. And what I want to do, I want to show you why this formula works, and then we'll look at an example of how to use it. Now, Cramer's rule is kind of a generalization of the elimination method. So let me illustrate here. Let's just look at these two equations. We have equation 1 here and equation 2. And let's suppose I want to use the elimination method and eliminate the y variable. Well, what I'm going to do then is I'm going to multiply equation 1 by b2, because what I want is in both of these I want b1, b2, but I want one of them to be the opposite. So I'm going to multiply this equation by b2 and this equation here by negative b1. Now when I do that, what's going to happen is that's going to give me a positive b1, b2 up here and a negative b1, b2 down here. So let's see what this looks like. There's the first equation, and here's the second. Okay, see, I just multiplied through the first one by b2 and the second one by negative b1. Now let's add those. Let's just add those. And you'll notice that the y's have been eliminated. And here's what we have. Now, I want to factor out an x over here, because remember, I'm trying to solve for x. I eliminated the y's, now I'm going to solve for x. So here we go. I factored out the x, and now I just divide by this. See? There we go. So this is what x equals. This is a generalization of the elimination method. Now if you notice though, this top thing right here and this bottom thing right here, these are determinants. In fact, I could write the top as the determinant of C1, C2, B1, B2. So take a minute and dig this. Look, if I want to find the determinant of this, I go C1, B2, see there? That's that right there, minus B1, C2. See? That's right there. See? So yeah, I could just, instead of writing this, I could just write the determinant. And then down here, look at this. I could write this bottom as this determinant. Notice, A1 times B2, see? Minus A2, B1. See? So in other words, I can rewrite this as the determinant, and you might say, well, why would you want to? Well, that might help us to remember the technique more easily, because this up here, this might be kind of hard to remember. But look at this. Look what's on the bottom here, this bottom determinant. It's just the coefficients of this left-hand side here. Look, A1, B1, A2, B2. See, look at that. A1, B1, A2, B2. And look at the top. The top is just like the bottom, except this column for the x's has been replaced with what's on the other side, C1, C2. So in place of the a's, I've got C1, C2, and then the y's are exactly the same. So this makes it very easy for us to remember. Now, you might say, well, what about the y's? Well, we could go through this same process to figure out what the y's are. The formula for the y's would look like this. Notice the bottom is exactly the same. It's just these coefficients, A1, B1, A2, B2. See? Just the determinant. But the top, since I'm solving for the y, I replace the y column. The column where the y's would go, I replace that with C1, C2. And then the x's are the same. See? Now, we can generalize that to more than just a 2 by 2. You know, 2 equations, 2 unknowns. We could go 3 equations, 3 unknowns. Heck, we could go 10 equations, 10 unknowns. Cramer's rule would work for all of those. So let's generalize this. Notice for this 3 by 3 system, we have on the bottom the coefficients, A1, B1, C1, A2, B2, C2, A3, B3, C3. See? Just like this. Now, if we're trying to solve for x, I'm going to replace the column of the x's with what's over here. D1, D2, D3, see? And the rest looks the same as the bottom. See, the b's are still there, the c's are still there, but where I'm trying to solve for the x's, I replace those numbers with these numbers over here. Now, the same for the y. Look at the y's. Bottom, still the same. However, look at the top. In the column where the y's would go, the y coefficients, I've replaced those with these numbers over here. And likewise, the z. Now look, the column with the z's, that's been replaced. Okay? So let's look at an example. Let's suppose that we have this system of equations, and I want to solve for x. Well, here's the setup. Notice the bottom. I've got 2, 5, 7. See? 2, 5, 7. 9, negative 4, negative 2. See? 1, 3, 6. 1, 3, 6. So it's just the coefficients over here. But up at the top is going to look the same. Notice 7, negative 2, 6. 7, negative 2, 6. 5, negative 4, 3. 5, negative 4, 3. These columns are the same, but I'm solving for the x's. So I replace the column where the x's are with this, negative 3, 27, and negative 6. Let's see what that is. This bottom, and I just used my calculator to find the determinants. The determinant of the bottom is negative 99. The determinant of the top is negative 297. And if you work that out, you just get 3. Okay, so there you have it. Now, I'm going to solve for y now. And notice, I've already calculated this determinant on the bottom. It's the same for all of these. I found it to be negative 99, so I'm not going to do that every time. I've done it once, that's good enough. So I'll put it down here. Here's negative 99. But up top, notice I've got 291. The x's are still there, 291. However, the y's, I've replaced those with negative 3, 27, negative 6. See that? And then the z's are the same, 7, negative 2, 6. And there we have it. We get negative 99 over negative 99. That is 1. Okay, now let's look at the z's. Okay, still, I just kept the negative 99 down here. The x is 291, y is 5, negative 4, 3, but the z column, where the coefficients of the z's are, they're gone. And I put negative 3, 27, negative 6. So let's see what that is. 198 over negative 99, which is negative 2. So there you have it. We've solved this system of equations and found the answer to be 3, 1, negative 2. That's the ordered triple. 3, 1, negative 2.